Alrighty then, corn children. Yes, here it is. Part 3. Volume of Revolution, Disk Method, Part 3. And here's where this is going to get crazy, people. We're going to integrate with respect to the variable y. Yeah. Woo! I bet you wanted to see that. Alright, here we go. Here's our problem. It's easiest if we work through an example together. I am going to be using technology again, so I'm going to be using a graphing calculator to actually do the integration, but that's what we're up to. So grab a paper, grab your calculator, pause it if you need to along the way. Here we go. We are instructed to find the volume of a solid formed by revolving the area bounded by y equals e to the x, it's your exponential curve, y equals 4, horizontal line, x equals 0, also known as the y-axis, about the y-axis. All right, so here's the deal, people. In volumes 1, 2, and 3, or 1 and 2, parts 1 and 2, we were revolving around a horizontal axis of revolution. The axis of revolution has now gone vertical. So in the other videos I mentioned that when our axis of revolution goes one way, our rectangles need to go perpendicular to it. Perpendicular, people. So here's the deal. Yeah. This time, our area will be thought about as stacking the rectangles vertically on top of each other, and when we revolve them, this time the discs that are formed are horizontal discs, and the height is a small change vertically. The small change here is not a horizontal change, it's uppy-downy. It's with respect to y. No. Yes. Now, the good news is our volume is still going to be found by integrating a radius squared, but this time with respect to y. Because this is with respect to y, the radius will need to be a function of the variable y, and the limits of integration will need to be y variable limits. I'm missing an I in there. All right, let's start with the limits. The limits are actually pretty easy in this particular problem. When we stack these rectangles, the lowest we can go would be that value. Well, what's that value? Well, where does e to the x cross the axis? Oh, that's at a height of 1. Now look, it's the y coordinate. The y coordinate that becomes the limit of integration. What's the highest these will stack? Well, y equals 4 is where the area stops. So those are y limits, limits found on the y-axis. All right, it is indeed going to be with respect to y. Our radius squared needs to be y stuff. Now, in some of the previous videos, I gave you some helpful hints on finding the radius. They're still true here. No, yeah. I would like for you to put your finger on the axis of revolution. This is what we're spinning about. Put your other finger as far away as you can go on that rectangle. This will be our radius. Now, instead of top minus bottom to figure out what this expression is, we're going to do right minus left. Our right curve is on e to the x. Now, hold your horses. This is going to be a problem. I'm writing e to the x, but that's a problem. Minus the other curve is x equals 0. Now, I don't know if you noticed this, but this is a problem. This is not a function of the variable y. This is a function of the variable x, and we must have a function in terms of y. So I need for you to look at that equation with me. I need to solve this equation for the x variable in terms of the y variable? Well, the simplest thing to do would be to take the natural log of both sides of that equation. Now, that doesn't always work. It works because the right side is e to the x. Natural log of e to the x is x. So instead of using e to the x here, we're going to use natural log of y. Another way to describe this curve instead of y equals e to the x is x equals natural log of y. That, ladies and gentlemen, is our radius. No way! Yes way. So again, it's right minus left, but as a function of the variable y. No, I'm not going to write the minus 0. That's silly. So this is the natural log of y. All right, now, this is not something that's a basic integral, and that's why we're going to be using technology. Now, I can type this into my calculator with the y variables in there, but I think it's probably easier just to switch these out when I type and type them with x variables. Now, we do need to be careful about how we enter this. Remember, on the graphing calculator, it automatically puts parentheses. So it's kind of a parenthesis fest here is what we've got going on. So let's go ahead and type this in. So I'm going to get rid of that. And let me bring it up here so we can all see. I'm going to go to the integration feature on my calculator. Come on, focus, focus. There we go. I'm going to integrate from 1 to 4. Now, the radius is squared, so I open a parenthesis. I am typing the natural log, which opens another parenthesis. Even though it's technically y, I use an x just because it's easiest. Close the parenthesis for the log, close the parenthesis for the radius, and then square that. All right, do you see all of that? And then we're going to integrate, even though technically it's y, it's just easier to type with x. So I've typed it all in. Please notice, though, I did not type the pi. You see that? There's no pi. So when I hit enter, the radius is that times pi. So if I write that down, 2.59, if I round at the third decimal place, with the pi symbol, or if you prefer, focus, focus, focus. If you prefer, you can take your answer on your screen and multiply by the pi button. So the equivalent for that, 8.158. Either of these are acceptable, 3 decimal place accuracy. All right, so that is a little bit more challenging. We, again, had a vertical axis of revolution. Therefore, we had a horizontal, perpendicular to it, a horizontal rectangle, which when spun became a disc-oriented that-a-way with respect to y. It was imperative then that our radius is right minus left, but the right curve had to be rewritten as a function of x equals y stuff, a function of y, x equaling the y stuff. That was used in our radius. All right, please enjoy that, and I will look forward to assigning you some homework in the future. I hope you look forward to it too.